Welcome to my Introduction to Networking course, also known as ITN. This is the version 7 material preparing learners for the Cisco CCNA 200-301. Cisco curriculum, everything is owned and copyrighted by them. Module 12, IPv6 Addressing. So we're going to be looking at, first of all, what are the issues with IPv4 that made us move to IPv6? We're going to talk about IPv6 representation, addressing type. Then we're going to look at the types of addressing, global unicast addressing and link local addressing, similar to private versus public addressing for IPv4. Then we're going to talk about the dynamic addressing for public unicast addresses in IPv6. But that's not all. We also then will talk about dynamic addressing for link local addresses, multicast addresses, and then we're going to talk about subnetting in IPv6. Though subnetting in IPv6 is way simpler than subnetting in IPv4. So jumping right on in, IPv4 issues. In the previous lecture, we talked about the different words that actually assigned our IPv4 addresses. And that meant we're also looking at how many addresses those words gave the different groups. How many were sent to North America, South America, Africa, Asian Pacific, and Europe and Russia. Well, the problem with that is these addresses were exhausted already. You'll notice a lot of these dates are 2015, 2012, 14, 11, 2020. All of these have already passed. So that means almost every country has already exhausted all of their IPv4 addresses. Hence the need for IPv6. IPv6 has a much larger address space. IPv4 was 32 bits, and that gave us roughly 4 billion addresses. Well, IPv6 is 128 bits, and that gives us roughly 340 undecillion addresses. So why do we need so many addresses? Well, one, before we had a typical house having 5 to 10 IP allocated devices. But with the growth of IoT, with the growth of smart devices, we're now seeing homes needing 50-ish addresses. Smart TVs, smart refrigerators, smart washer dryer, IoT-based cameras, smart TVs, and so forth. So we needed something that was going to give us additional addresses. So why the drastic jump between 32-bit and 128-bit? Essentially, they wanted to ensure that there was plenty of addresses for growth. So we wouldn't have to do this in the next 20 years again. IPv4 and IPv6 can coexist. You can have both running simultaneously. This is called dual stack. You can also have an IPv4 network transmitted over IPv6 and vice versa. Those technologies are called tunneling and translation. If we're looking at transporting an IPv6 packet over an IPv4 network, that's tunneling. If we're talking an IPv6 enabled device communicating with an IPv4 enabled device, this is called translation. So let's go ahead and let's talk about address representation. How do we represent 128 bits? We no longer do this in binary. We actually do this in hexadecimal. The IPv6 addresses are not case sensitive, so uppercase, lowercase doesn't matter. It's all the same. The preferred format for writing an IPv6 is there will be 8 groups of 4 characters separated by colons. This is called a hextet. And again, this is unofficial. 4 characters per hextet because each character is a base 16 number. It's a hexadecimal number, or 4 hexadecimal values. So for example, we have 8 strings of numbers, with each string being separated by colons. So 2001 is the first hextet, 0DB8 is the second hextet, and so forth. So you'll notice we have a large string of zeros also. So that makes writing these addresses a little harder. So there are rules that we can look at when talking about our addresses and how they are displayed. So rule number 1, when we have a long set of zeros, we can actually remove leading zeros. When we have an entire hextet full of zeros, we can, in one of them, shorten them. And that's actually rule 2. But sticking with rule 1, only leading zeros can be removed. So here, when we have a long string of zeros, 2001, 0, DB8, 000, well, those zeros can actually be just shortened to 1 0. And in the 5th, 6th, and 7th hextet, you'll notice again all zeros. So we have that long string of zeros. With that long string of zeros, we can actually remove them and replace them with double colons. So colon is a way to denote all zeros in those areas. We know that there are 8 hextets. So when we see a double colon, that means all of the remaining hextets between those double colons are zeros. So first and second and third hextet, actually I'm going to grab my pen so we can do that. First, second, third, fourth hextet are all zeros. And the 8th hextet is that 200 number. So that means the remaining 1, 2, 3, 4, the remaining 3 hextets in that double colon are all zeros. Again, this is 8 groups of hextets. So 1, 2, 3, 4, and we had that one. So that meant the remaining 3 hextets of all zeros were replaced by that double colon. You can only use a double colon once. That way there is no misconstruing what those double colons mean. If we had double colon, a hextet, and double colon, we don't know the number that would fall in between each set of the double colons. That is why you can only use them once. Alright, moving on is address types. In IPv4, we talked about characteristics, multicast, broadcast, unicast. Well, in IPv6, we have unicast, multicast, and anycast. Unicast and multicast are pretty similar. We no longer have broadcasts. That has been replaced with an anycast. Anycast basically is any IPv6 unicast address can be assigned to multiple devices. Basically, a packet is sent to an anycast address is routed to the nearest device having that address type. So you can have multiple IPv6 addresses assigned to devices. So unlike IPv4, IPv6 doesn't have a broadcast address. We already know that. There is a IPv6 all-node multicast address that essentially is the same thing. So there's an all-node multicast that will act like a broadcast. Address types, we have to talk about prefixes. So again, here we have, similar to IPv4 when we talked about networking and host bits, here we have a prefix and interface. When we're dealing with the prefix, that is typically the first 64 bits of the network. That's what we would classify as the network bits. The interface ID is very similar to the network. Prefix is going to be the network. Interface will be the host bits. It is strongly recommended that when we're dealing with 64-bit interface IDs for most of the networks, this is basically done because SLAAC, stateless addressing auto configuration will use 64 bits for the interface ID. Makes it a little easier. Also, it splits the addressing in half. So the first 64 bits will be given to the network portion. So types of addresses. With a IPv6 unicast address, we have several special types of address. A global unicast address, GUA, G-U-A. We have a link local address, LLA. We have our traditional loopbacks, unspecified addresses, unique local addresses, and other embedded IPv4 addresses. The large two that we need to understand the most are global unicast addresses. This is most similar to IPv4 public addresses. They're unique and internet routable. And we have to understand our link local addresses. This is required for every IPv6 device on the network. And basically, link local addresses are not routable. And these are very similar to private IPv4 addresses. The nice thing with IPv6, it does have a unique local address ranging from FC00 to FDFF. So that entire range, FC to FD, have a very specific functionality. This is going to be more of the private addresses for IPv4, but they're not exactly the same. I understand that link local addresses are also similar to IPv4 or to the private addresses, but again, they're not quite identical. Here, FC to FD are going to be the most like private addresses. They are unique local addresses used for local addressing within a site or between a limited number of sites. Unique local addresses can be used for devices that will never need access to another network. Unique local addresses are not globally routed or translated to a global IPv6 address. That is the key takeaway. These types of addresses cannot be translated to a global address, where a link local address can be translated. Looking at an IPv6 GUA address, basically, it was designed in such a way to allow a very limited number of GUAs to allow on the internet at this time. Basically, we are looking at the first 3 bits of any IPv6 address. So only the first 3 bits that begin with 001 are allowed to be assigned. That means they will start with 2000. Currently available GUAs with a decimal of 2 or 3 are allowed. Basically, that took all of our addressing, and that means only 1/8 of the current addressing space is allowed on the internet. This is done on purpose. This means that there's plenty of room for growth. They're not just wasting addresses for the sake of wasting addresses. Normally, global unicast addresses will start with 2000. Alright, the GUA structure. We have our global routed prefix. That should be our first 64 bits. We have a subnet, and basically the subnet field is with the area between the global routed prefix and the interface ID. This is used to organize the overall addressing space and identify the appropriate subnets within that location. The interface ID is the remaining 64 bits, and that's going to be more of the host portion. So the prefix can actually be the prefix and the subnet length. Those combined will be the first 64 bits. The remaining 64 bits will be the host bits or interface ID. Moving on, we have to understand our link local address. Our link local addresses Basically, packets with the source or destination of a linked local address cannot be routed. They have to be sent to a default gateway. If it needs to leave the network, it will be masked to a global unicast address. Every IPv6 enabled network will have a linked local address. If a linked local address is not configured on the interface, it will automatically create one. Basically, linked local addresses are in the FE80 range with a prefix of /10. That means the first 10 bits do not change. Realistically, FE80 is what you would always see as the beginning for a linked local address. And that is this chapter in a nutshell. If you have any questions or concerns, please reach out.